So these exercises are grouped by 3 for a reason, because each of these 3 exercises that you see, these grouped exercises, are having you try to arrive at what's going to be called a log property. And so we chose the log so that, number one, we could do it in our head or with what we already know from our work on Friday, in Friday's class. So we learned in Friday that if we could write log base 2 of 32 as log base 2 of 2 to some power, like this, that since we have an exponential function 2 to the 5th composed with its inverse function log of the same base, LO stands for lift off. All we have to do is lift off the exponent, and that's our answer. So log base 2 of 32 is exactly the same as the exponent 5. So again, when you look at this, I want you to get used to seeing the exponential function composed, because it's the input here, into your inverse function. So what this looks like is this. That's what it looks like, and it brings you right back to x. Because f of x in this case is 2 to the x, and f inverse is log base 2. So anytime you compose inverse functions, and in this case an exponential with its inverse function, the log of the same base, you just lift the exponent off, you're right back to where you started. So we know the answer to that first one is 5, and if we use a similar approach to this product here, this sum, we can say log base 2 of 8 is 3, because 2 cubed is 8, and log base 2 of 4 is 2, because 2 squared is 4, and lo and behold, we get the same answer. So what Caitlin and I were hoping that you would see when we created these exercises is, since we can write log base 2 of 32 as a product, now there's several products you could write this as, 16 times 2, 8 times 4, but we broke it up to be the same as log base 2 of 8 times 4. So what we were hoping you would see is the relationship between this part of number 3 to what we found in number 2, and how that relates back to number 1. So if we look at this, log base 2 of 32 is written as a product. So we call this, remember, just again working on a vocabulary, that's called a product. So the log of a product can be written as log base 2 of 8 plus log base 2 of 4, because all 3 of those represent the same thing as the number 5. So if you have the log of a product, it's the same as adding the logs of each of those factors. Now, why does that make sense? So where does that come from? Remember, each of these represent exponents. What are the exponents? Well, 8 times 4 is 32. 8 is 2 to the 3rd, and 4 is 2 squared, and we know that equals 32. And if we use our exponent rules, we can write 2 to the 3rd times 2 to the 2nd as 2 to the 3 plus 2. Notice, when we use exponent properties, we must have the same base, and if we're multiplying exponentials with the same base, we simply add the exponents. So since logs are exponents, there has to be some relationship between exponent properties and log properties. And here it is right here. If you're taking the log of a product, the base is the same. The base is the same. You simply add the individual exponents. So the individual exponents here would be log base 2 of 8 and log base 2 of 4. So the better you know your exponent properties, the better the log properties are going to be. Yeah, Nick?
So instead of 8, 4, it was like, like 3x plus something else or whatever, you can do log base 2 of.
So Now you're going into a more general case. So if it was log base 2 of 3x, okay, this is a product. Yep. And we can't prove it because we can't do the actual math out like we just did. So yes, this would be log base 2 of 3, which is your very first factor right here. Your first factor is your first exponent. There's your first exponent. That's just an exponent. And you add to it log base 2 of your second factor, x. So if we knew what x was, we could get the answer here and we could smush them together, but we don't know what x is, right? Any product with the same base, the log of any product is the sum of the factors. So if you had 6 factors here, like a, b, c, d, e, f, then it would be the log base 2 of a plus the log base 2 of b plus the log base 3, blah, blah, blah. Right? So yes, any product, doesn't matter what it is. Now you say, well, what if I didn't feel like picking 8 times 4? Suppose you said log base 2 of 32 was equal to log base 2, and let's suppose you did 16 times 2. Well, you just better come up with the same darn answer or something's wrong with math, right? So let's do this one out using the idea we just saw. So we're taking the log of a product. So we know it's the sum of the individual logs. So let's see, log base 2 of 16 plus log base 2 of 2. And the log base 2 of 16, if we had to do it all out, could be written like this. And the log base 2 of 2 would have a 1 up there. So my only job here, here's my exponential function, 2 to the x, and I'm composing it with its inverse function. I just take off the exponent 4, and similarly here 1, and I still get the same answer. 4 plus 1 is 5. Okay, so this is your very first log property, and hopefully you can see its relationship to the exponent property right here. So when you're taking the log of a product, same base, it's the sum of the logs of each of those factors, whatever they happen to be. Okay? So this is your first log property. And the analogous exponent property would look something like this. B to the x times b to the y. There's your multiplication problem with the same bases, and you simply add the 2 exponents. And that's what you're doing here. You're adding the 2 exponents. All right, so let's take a look at the next one. So I'm just going to get rid of this page now that we've answered. Next question. Okay. So the next one says we've got the log base 2 of 16, which we know the answer is 4. And then suddenly I've thrown in this mysterious new problem, number 5. And we see that the answer here is 5 take away 1, which is 4. So what conclusion can we reach? Well, we know that log base 2 of 16 is the same thing as log base 2 of 32 divided by 2. And that's exactly the same as this. Log base 2 of 32 take away log base 2 of 2. So now we have a new property. The new property says if you're taking the log of a quotient, the log of a quotient, remember quotient is the word we use for division, right? The log of a quotient, you take the log base of that base, same base of the numerator, and you subtract the log base 2 of the denominator. They're all equal to 4, all 3 of these. And again, if we try to make a relationship back to our exponent properties, our exponent properties for this particular problem would look like this. Well, 32 divided by 2 is 2 to the 5th and 2 to the 1st. And when we divide exponentials with the same base, what do we do to the exponents? Subtract them, absolutely. And that's why we subtracted the logs. Logs are just exponents. I know, it's a really fancy, crazy, confusing way to write them, but that's what we have. So that's our second exponent property on this next page. If you have the log of a quotient, you simply subtract the log of your numerator, the log of your denominator from the log of your numerator is how we would say it. Or the log of the numerator, take away the log of the denominator. Whatever your base is, must be the same. So notice, there is no multiplication of logs on the right side, and there's no division of logs on the right side. If you have multiplication of logs, you end up adding. If you have division, you end up subtracting. Again, I would have what I'm writing here in purple on my cheat sheet for my test on Friday or for my final, because if you can simply say to yourself, what did I do with exponents? That's what I do with my logs. If I added my exponents, it meant I was originally multiplying. So if I see a log with a multiplication as the input, I just add the individual logs. If I see a log with a division problem in it, I subtract the log of the numerator and the log of the denominator. I do the same thing I do with exponents. Now the last exponent property is one, this next group of three is probably the one that you will use the most throughout the rest of the class, particularly when we start working on application problems with exponential functions and logarithmic functions. This property will be, and also solving equations that have exponentials and logs in it. This property will come up over and over and over again. So I assume that most of you, if not, let me know, found that the answer to this was 4. And the answer to this was 2 times a new 2 here, this 2 being the answer for this. And so what can we conclude about log base 3 of 81, which can be written as log base 3 of 9 squared? They're both equal to 4, and so isn't this, 2 times the log base 3 of 9. So this one is kind of a fun one if you want to think of it as fun, but maybe you don't want to think of it as fun. Notice that log base 3 of 9 just stands for the exponent 2, because 3 squared is 2. And then this other 2 out in front was also an exponent. So you're multiplying 2 exponents here, because to simplify this, the 2 just comes down in front and multiplies the remaining exponent, log base 3 of 9. There's your 2 times 2. So here you're multiplying 2 exponents. So what were you doing in the world of exponents to multiply powers? Well, that was this exponent property. When you had a power and you raised it to another power, remember, you simplified that by keeping your base the same and multiplying your powers. So here you have a power, log base 3 of 9 represents a power, and you're raising it to another power too. So you simply multiply the 2 exponents, just like you did here. So the relationship between your log property and your exponential property holds. In the past, Caitlin and I would just show you like mathematical proof for why these worked, but decided not to like put any more information into your brain that you don't need. But it's really nice to see how this really happens. So if you're interested in that kind of thing, sometimes I have people that start in 107 and they become math majors. So if you're interested in that, let me know. So this is how it looks. You have log base b of a power. Notice the p just goes down in front and multiplies the remaining exponent, log base b of x. And again, that comes from this relationship back to exponents. Now I'm going to put a big line across here because I don't want you confusing these 3 properties with the next thing I'm going to show you. So separate those out. Again, notice, I'm going to keep saying this. In your original log problems in 1 and 2, you saw multiplication and division. You didn't see any multiplication and division on the right-hand side. However, you do in number 4 see a division of 2 logs. And that's only going to happen when you're asked to evaluate a log that you have no way of doing either mentally in your head, like log base 5 of 32, we can write as log base 5 of 2 to the 5th and get our answer. And you can't use your calculator to do it. That's the only time you're going to see this division of two logs. You'll never see it in using any of these properties. So that comes down to the last group of three here, of four here. Log base 5 of 125. Again, we're using something you could do in your head. That's 5 to the 3rd. So I'm composing two inverse functions. I'm right back to where I started with the 3. I lift off that exponent. And now what we're going to show you is this special property of logs. So let's pretend that we could not get the answer 3 for this. Well, we also cannot put this into our calculator because our calculator only has two buttons, only evaluates two types of logs. LOG for base 10, that's our common log, and capital LN for our natural log. So I can't put in log base 5, it's impossible. So what we do is we convert log base 5 of 125 to be the natural log of the numerator divided by the natural log of the denominator. Notice this is the only time you see the division of two logs, is when you're trying to find a log with a base that we can't actually compute either mentally or with our calculator. Now I can find the log of both of these in my calculator. I just press ln and I put 125. And then I put division, ln of 5. And that's 3. Well,
If it wasn't some odd number that didn't break down easily, like 5 and 1, like 12, 28, and 3.5 or something. That's still work.
yes, this will always work whenever your base. In other words, we know the answer to this because we can compute it. Even if it was something we couldn't compute, this always worked, where you take the natural log of whatever's in your numerator and you divide it by the natural log of your base. But what's really more interesting, I think, to think about, and for those of you who like these kind of things, it also works to take the common log of the input, so log base 10 of 125, and divide it by log of 5, log base 10 of 5. It doesn't matter whether you take the natural log or the common log, you get exactly the same answer. Now, why that works is an interesting thing for you to think about. And I don't want to ruin all the fun by giving away the answer, but there you go, same thing. So the moral of the story is, if you have a log that you're asked to evaluate, and the base is not 10, and the base is not E, you can convert it using this property by taking either the common log of the numerator dividing by the common log of the base, or the natural log of the numerator divided by the natural log of the base, and get the answer that you need. So that's the fourth property that we gave you. Okay, the fourth property is written as log base b of x. Now notice, we don't know how to take log base b of x, so we convert the right-hand side to a log we do know. A is either 10 in this case, so in this case, A is either 10, so we're using the common log button, LOG, or A is E, and therefore we would use the LN button, the natural log. So A is either 10, or A is E. I guess I missed my little is in there. A is, okay, or A is E. So those are the two we get to use. So if I just gave you this random thing like this, log base, I don't know, 17 of, well, let me use something that we could at least estimate instead of being silly. So let's do log base 5 of 37. Okay. So this is asking for the exponent that you raise 5 to get the number 37. That's what it's asking. What power do I raise 5 to get 37? Well, there's no way, I mean, unless I'm a math savant, that I would know that answer, right? But I can estimate with what two integers the question mark falls between. What two integers would the question mark fall between? It's got to be, yeah, 2, 2, and 3. Because I know 5 squared is 25, 25 is less than 37, and 5 cubed is 125, which is bigger than 37. So it's got to be some number between 2 and 3. So this is where your calculator would help you out. You could just throw that right into your calculator, at least before you even start. Oh, let me get a picture of this and put it on the other page so you have it for your notes. Here for a minute. Next page. There you go. So that's that right there. All right, so if we were doing this problem, we would just pull out our calculator, we clear it out, and we say, okay, I don't know, I don't have a log base 5 button on my calculator, so let me use my favorite. My favorite is the natural log. So I'm going to take the natural log of 37, and I'm going to divide it by the natural log of my base, 5, and let the calculator do all the work. And there you go. Okay. So I can only approximate this answer. If I was doing a calculation and I asked, and let's say this was the end result of this calculation, like solving an equation, this would be the exact answer. If I wanted you to approximate it, then you throw it in your calculator and you'd say it's approximately 2 point, and I wanted, say, 3 decimal places, then you would write something like that. Okay. So that's using your log property to estimate the value of log base 5 of 37. And again, it doesn't matter whether you do common log. So if common log's your favorite, the common log of 37 divided by the common log of the base. Voila, same exact problem. Okay, same exact. They're not the same, right? Common log is base 10, natural log is base E. That's what I'm saying is an interesting thing for you to think about. And that's the kind of thing, if you want to chat with me about it, I'd love to chat with you about it. Okay. But to show you why that works would introduce, well, for some of you, fun stuff, for some of you, unnecessary stuff at this point in the semester to like be in your brain. You're just trying to stay afloat with the idea of logs to begin with. So, all right. So let's now use the properties to expand and simplify, condense. And what do we mean by that? If you look at this first log property, we call the right-hand side of this expansion. We're expanding here. So when we go in this direction, we're expanding. When we go from the right-hand side to the left-hand side, we're condensing or simplifying. That's what we refer to in mathematics. So when you square a binomial or you raise a binomial to some power, you're expanding it. So, and then when we go back, we're representing it. Some people wouldn't call it a simplification. They would just call it a condensed form. So in other words, when we see something like this, x squared plus 6x plus 9, and we write that as x plus 3 quantity square, going in this direction is condensing it using your definition of exponents. Going in this direction is expanding it. Yes, expanding a binomial. So I once saw this really cute. Oh, never mind, I won't tell you. All right. So use the properties of logarithms to expand and simplify the following expression. So first we want to expand it, and then we want to, if possible, look at each term in our expansion and see if we can simplify it. So the first thing I do here when I see something big like this input, the input here has lots of things going on. So just like when I used to do order of operations, and I would say to students, if you had this really big, long, complicated expression, I would say, what is this? Is this a multiplication problem, division problem, adding some problem, subtracting? And students would look at me and I'd say, well, what would be the absolute last operation you would perform? So if you knew a little teeny value for x, say 2, and a value for z like 1, and a value for y like 3, and you were plugging in those individual values for each of them, and you performed all the operations that is going on in this input, what would be the absolute last operation you would do? What? Multiplication, and Ken says division. All right, well, let's just take a quick peek. Let's make this as easy as possible. Because, let's say x is 2, and y is 1, and z is 3. Let's suppose. And I wanted to evaluate this input. And because I'm just trying to figure out, is this a multiplication problem or a division? Those were the two answers I heard. So I'm going to throw in a 2 for x, 3 for z, and a 1 for y. So on top, I would do my exponent first. You don't have to write this down, folks. This isn't like really generic to the. So what would be, I'd do my multiplication next. I'd get 300. And what would be the last thing I'd do here? Division. So this is really a division problem with a lot going on. Okay, because it's the last operation I would perform. So why am I even telling you this? I'm telling you this so that you can look at your input and identify the property, the first property you're going to use, the first log property. Because your log properties are based on multiplication, division, and then a power raised to a power. So when I look at this, the first thing I see is division. So what I want to do is I want to say, okay, I'm going to be subtracting the log of my numerator and the log of my denominator. That's the first property I'm going to use because it's a division problem. Okay. Now I have to go in and individually deal with each of these terms. Okay, again, remember, terms are the parts of an adding and subtracting problem. So I turn this division problem into a subtraction problem. So now each of these pieces are called terms. And so you have to come to terms with this, so to speak. Ha, ha, ha. No pun intended, but it's kind of cute. All right. Basically, you're going to come to terms with this by expanding this product, which is going to be a bunch of terms, a bunch of plus signs. So now I take each one individually, and now when I say what kind of problem is this, Mahendra's answer is right. This is a multiplication problem, the 25x squared z. So I'm going to take the first property of logs and I'm going to use it here. So I have log base 5 of 25, and I'm going to take that and add it to the log base 5 of x squared, and then I'm going to add it to the log base 5 of z, because my first property says that if I have the log of a product, then I simply add the log of each factor in that product. So I've got 25x squared and z, and there they are. So this thing expands out to 3 separate individual terms, and then I'm going to subtract from that log base 5 of y cubed. Okay, so notice if I wanted to, I could put like brackets or parentheses here just for you to see that that was the original numerator. There it is. There's 3 separate individual logs. Now the question is it possible for me to simplify any part of these individual terms? Well, yeah, because I haven't even finished simplifying this log in this log, because this is a power to a power. So I've got to use property 3 on this one. So let's identify the properties. We'll write them right above it. at each step. So the first thing I did was I used property 2. Right here, property 2. Then here with all these arrows here, I used property 1 to get each of these individual terms. And now on these two, I'm going to have to use property 3. So let's just rewrite each of these boxes as they are. We won't simplify them yet until we finish using all of our properties. So here I've got a power to a power, so this power comes right down in front, the 2 comes down and multiplies what's left once I take off that 2. There we go. And I have log base 5 of z. And then again, I have another power to a power, so the power, woo, comes right down in front, log base 5 of what's left once you pull off that power. It's log base 5 of y. So now I have used all 3 of my exponent properties, and now the only thing I ask myself is, can any one of those terms be simplified? Well, the very first term can be simplified. Log base 5 of 25 is what? 2. And then I just rewrite everything else exactly as it looks. So this is the expansion of that original log. You've expanded it out. All right. So that would be your final answer right there. All right. So if you can do it one way, you should be able to go the other way, right? You want to go both ways here. So now we're going to condense an expression that has a bunch of terms in it and back into the log of either a quotient or a product or a combination of the two. Maybe has some powers, 2 powers in it. We don't know until we actually look at the expression. So the first thing I do here is I individually box out each of my terms like this. I box them right out. So I know each one of those I'm going to rely on right now. If I want to see if there's any way I can simplify each one of them. Well, that's how some people might start. Other people might say, well, when I see that subtraction and when I see that addition, I know that I'm going to have multiplication and division going on. So some people might start by doing this. It really depends. Some people may start by just keeping each of these terms and saying, I know I would have to do this multiplication and then do my division. So some people might sort of group them like this. So they know that those first 2 terms are going to involve the log of a product. And then you know that, so you know you've got some kind of multiplication going on here. And then with that subtraction, you're going to end up dividing. So that's sort of like seeing, you know, the overview of the problem. So in my mind, and again, you want to do it in pieces most likely, but in my mind, I know I'm going to have something like this. I'm going to have the log of a division, a quotient. And then I deal with what is my numerator individually and what is my denominator individually. But just like when I started off with this original problem up here and said, what would be the last operation I would do here? And the answer was division. The same idea here is the last thing I would do here, if I had numbers for x, z, and y, and I put them in, the last operation I would do here would be to subtract. So therefore, I go right there and I put my division symbol. All right, so let's take a look at each of these little red boxes called terms individually and see what property we can use. So the first thing I notice here is I've got a 3 and it's multiplying a log. So that means I'm multiplying exponents. And I only multiply exponents in property 3 when I raise a power to a power. So I want to hook this 3 right back there and put it back on the x. So it's log base 4 of x to the third power. So there's my 3. I'm going to put it right back there where it belongs. So I'm working backwards now. And I still have this little plus sign. And now I'm going to take that 2 and knock it right back there. Log base 4 of z square. So it just comes back on, attaches itself back up there. And similarly, so won't this 1/2 power, which is the same as the square root. But given that we're working with logs and exponents, I'm going to keep everything. I'm not going to revert to making things radicals. I'm just going to keep them as exponents. So w to the 1/2 power. So this is what it looks like, log base 4. So this would be my first attempt. And let me actually make this exponent a different color as well. Okay, so the factors that were out in front of the logs now become the individual exponents. And now I just say, okay, the first thing I'm doing here is addition, which means originally that came from log base 4 of this product, x cubed times z squared. So I smush those back together. I add exponents when I was multiplying originally. My log property, I add my logs when I'm taking the log of a product. And now I subtract from that the log base 4 of w to the 1/2. And so now I have a subtraction problem of 2 logs with exactly the same base. Always keep your eye out to make sure it's the same base. So that means then this becomes the log base 4 of, this is my numerator, x cubed minus z squared, times z squared, over w to the 1/2. So that's how you would condense it right back, and you don't even need that times in there. You can just say x cubed times z squared. Okay. You could only if you put w to the negative 1/2. Yep, because it's in the denominator. Because this is the square root of w. So the square root of w can't turn into w squared. Other questions? All right, and then finally, we've already done one like this based on Nick's question. If you're asked to find log base 4 of 50, remember we can't do it in our heads. We have to rely on our calculator. So it's either the common log of 50 divided by the common log of 4, or the natural log of 50 divided by the natural log of 4, and that's it. Okay. So your test, your final in-class test for the semester is Friday. Wednesday, we're having a review, and I would like you to prepare for that review. I would like you to bring questions in to class and try to get here before 20 of and put your questions on the board, because the review is only as good as the questions that you ask. Now, the questions can come from any of the material, your homework, your project that you just got back, or your quiz that you just got back. Anything, or from your study guide for test number 3. Anything at all that's been, that you've been thinking about, or between now and Wednesday that you look over. Okay, I will not come in with questions prepared for you. This is your class. I had to take out my favorite class on data fitting so that you would stay with your review, even though we had that last snow day. So please use that time wisely to help you for the next test. Any questions about what's expected the rest of this week? Anything? Okay, so take your time and do, yeah, Rose? Yeah, yes, I'm sorry, 50 and 50. Yep, last one. Where are you seeing the what? Yes. You could, but I'm just saying, since exponents and logs are powers, then it doesn't matter. You could put it as 1/2, or you could write it like this: log base 4 of x to the third z to the second over the square root of w. It's just that everything we're dealing with is exponents, so we're going to write it. You're going to see it in an answer key or something to the 1/2. So as long as you know that these two are the same, it's okay with me. All right. Any other questions? Okay, so you definitely have some activities to do that should help you practice all of these different properties and use them expanding and condensing. And if by any chance you finish up early, you can start working on your study guide or go back and do some of those rational functions that you didn't get to graph yet, or some of the other class activities. There's plenty to keep you busy. And please just let me know if you have any questions. I'll be glad to help.